connect this audio. Can people hear me?
People back here.
Yeah, this doesn't seem to work very well.
Yes, I can hear you.
Okay. I'll just try to speak louder. So, yeah. Hi, I'm Sophia from Chicago, and I will be talking about fabrication errors, surface code, and modular triplets. So solid-state qubits, such as superconducting qubits, suffer from fabrication errors. If you look at the IBM devices that are available online, you can see both defective qubits and links, and these defects can come from various sources. One example is frequency collision, which applies to fixed frequency transmons, but in this study, we don't really limit ourselves to any particular type of defects. So suppose the goal is to make defect-free chips, then it's helpful to use a modular architecture, because with a monolithic architecture, for each defect, we need to throw away an entire chip. But now we only need to throw away a small chiplet. A prior work from our group showed how to do this and the trade-offs that are involved. But still, even with the modular architecture, the defects are still prevalent enough that the defect-free yield will still be too low. So we will need to use some of the defective triplets. Then the question is, given triplets with different defect distributions, which ones should we use? And to answer this question, we need to have a target application and to understand its performance in the presence of defects. We choose the rotated surface code as the target application because it's a popular choice for error correction. We're going to use red for the X stabilizers and blue for the Z stabilizers in this talk. So one way to adapt the surface code to defects is to use the super stabilizers. This approach works by forming large stabilizers around the defect, using the broken stabilizers as the gauge operators. For instance, in the top figure, a data qubit is broken, so the X super stabilizer consists of the two red triangles, and on the bottom, we have a larger super stabilizer surrounding a defect cluster. In both cases, the value of a super stabilizer can be computed from the product of the gauge operators. And since the X and Z gauges do not commute, they have to be measured in different rounds. On the top and the bottom, the codistance decreases by 1 and 2 respectively. The super stabilizers around larger defect clusters are subject to more measurement errors, so in order to more reliably read them out, we can alternate between the X and Z gauge operators less frequently. So before we move on to our main topic, let's do a sanity check. What happens if we ignore the defects and use them just like the good qubits? So if all we care about is the memory experiment, then this is actually fine. But defects can easily result in logical errors along the time dimension, which affects the logical operations. So a convenient way to see this is to use the stability experiment. Using this, we can see that a qubit has, when a qubit has more than 5 chips can be useful, which means we need to identify indicators to characterize the performance of the surface code adapted to defective arrays. And after this, we can estimate the resource overhead caused by the fabrication errors. All three of these goals require sampling a lot of random defect distributions and adapt the surface code to them. So we can't really manually do this, and we need to build a tool first. So the adaptation protocol has two so we need to deform the boundary to carve them out. The boundaries of the rotated surface code are quite delicate. For instance, if we have a defective syndrome qubit that's the same color as the boundary, which is the case on the left-hand side of the left edge, then we need to carve out a big chunk to maintain the color of the boundary. But on the right-hand side, we have a defective syndrome qubit on the right edge, but it's not the same color as the boundary, so we only need to carve out a smaller chunk. Another complication is we have to go back and forth between the two steps because the broken syndrome qubits can create larger defects in the interior, and then the resulting cluster could end up being too close to the boundary. Now we can move on to understanding the performance of the defective patches. Previous work did some limited numerical study. They compared the performance of the defective 13x13 patches, which end up having distance 9, with the distance 9 defect-free patches. In their plot, we can see that the defect-free patches seem to work better, even though all these patches all have the same code distance. However, this is an early work that's conducted before we had faster simulation tools and decoder implementations. So they only did enough shots for higher physical noise levels. And also they used the unrotated surface code and didn't use the shells for defect clusters. So we want to re-examine this result and this time focus on what happens when the physical gate error is below 0.2%, which is a more relevant regime for large-scale fault-tolerant devices. So when we plot the logical error rate against the physical error rate, we found that the defective patches actually have higher fidelity than the defect-free patches of the same code distance. And this plot is only showing one representative example from each code distance, but our conclusion is from a larger sample of defect distributions. And we see that there are straight lines in this plot when we plot both axes on the log scale, so we can use the slopes of these lines for further analysis. This way, we don't need to stick to a particular physical noise level. So if we put the slopes from multiple defective patches in one plot, we can see that the code distance is actually a good indicator for their performance, unlike prior work suggested. But for each code distance, there's still some variation. So next, we will try to explain the variance by finding a secondary indicator. So the code distance tells us the minimum number of physical errors that lead to an undetectable logical error, but the performance also depends on the number of such combinations. And we can approximate this by the number of unique shortest logical operators on a patch. This could be computed pretty efficiently, and this explains the variance well. And now we also know why the defect-free patches have higher errors than the defective ones of the same code distance. And this is because they generally have higher symmetry, unlike the defective ones that I show here. So our conclusion is defective patches are actually quite similar to their defect-free counterparts in the sense that their performance could be understood with the same indicators. And at the beginning, we also tried other indicators and they do not work very well. Here, I'm just showing one example. If we use the proportion of disabled qubits, then it doesn't take into account the location of the defect, so it doesn't work very well. And now we can finally estimate the resource overhead. We assume that each logical qubit is held by exactly one chiplet, which should be wider than the target code distance in order to tolerate some defects. And we use two defect models, one where both links and qubits can be broken, which is inspired by the tunable transmons with tunable couplers. And the other one only has broken links, and this is inspired by the fixed frequency transmons, where frequency collision is the dominant error. And to estimate the average resource overhead, we first need to compute the yield, which is the proportion of the triplets that can support a logical qubit of the target performance. So the left-hand side shows that when we use larger triplets, the yield drops more slowly as the defect rate increases. We define the factor of qubit overhead as the average number of physical qubits fabricated for a logical qubit, scaled by the case with no defects. This number depends on both the yield and the size of the triplets. So at different defect rates, the lowest overhead is achieved with different choices of the triplet size. So for these plots, we only have defective links. In this case, we can always disable the data qubits that are connected to them. But when we have both defective links and qubits, we end up with lower yield and higher overhead. One reason is qubit defects now lead to disabled syndrome qubits half of the time. And this can be mitigated by swapping the assignment of data and syndrome qubits. And this could be done either by diagonally translating the patch by one physical qubit or by rotating the triplet by 180 degrees. Previously, we have been using the defect-free distance 9 patch to set the target performance. Now we do this for different code distances and plot the resource overhead together. So this shows that the factor of overhead does not depend strongly on the target performance, but of course, it still depends strongly on the defect rate. So I want to mention an interesting complication. If defective triplets are not arranged well, then the code distance can actually drop after we merge neighboring patches in lattice surgery. So in this example, the code distance in each patch only decreases by 1 due to the defects if we look at them individually. However, if we merge them, they actually lose more than half of the code distance. But we checked that avoiding this kind of situation will not significantly lower the yield in the modular case. But you still might wonder, what if we use the super stabilizer on a monolithic device? Well, we won't be able to post-select in this case, so some regions of the device won't be able to support logical qubits that meet the standard. Our paper did a case study to show that if we use those suboptimal regions, then even a small proportion can significantly increase the program failure rate. But if we don't use them, we will end up having more constraints on compiling. And also, we won't be able to arrange the triplets to avoid the situation on the previous slide. So in summary, surface codes adapted to defects behave similarly as the defect-free counterparts in the sense that they can be characterized by the same indicators. And the modular architecture, together with the super stabilizers, can effectively mitigate the resource overhead due to the defects. The arrangement of triplets is important because it can affect the quality of the interactions between logical qubits. And it is still important to reduce the defect rate in order to lower the resource overhead. And finally, recall from an earlier slide, when a qubit has higher infidelity than its neighbors, but is not broken, we might still want to disable it. So yeah, now I'm happy to take some questions.
Questions?
Hi, Sophia. Great talk. I have two questions about your paper. So first, I was wondering if the yield model in the paper considers fixed frequency transmons. IBM is moving to these tunable coupler fixed frequency transmons. Do you expect that the yield will be better or worse for these types of qubits?
Actually, we were pretty agnostic to the particular mechanism of the defect. We just have two models, one considering that both qubits and links can be broken, and the other one assuming that only links can be broken. So yeah, these are not really something that we model.
Okay. Second question is, what challenges do you expect to see if you were trying to do the same thing for other types of codes?
Yeah, so for other types of code, I think these kind of approaches, I expect that they can be extended to other types of stabilizer codes. Sorry, I mean topological codes because they're local. But if we want to apply this to devices with sparser connectivity, the situation might be more complicated. And also, if we apply this to those non-local LTPC codes, I also expect the situation to be more complicated.
Okay, thank you.
Any other questions? We still have like a minute. No? Okay, yeah, thank you. Next we have so from the University of California.
Hi everyone, it's working. My name is Hezi Zhang. I'm from University of California, San Diego. Today I'll be talking about our paper, MECH, Multi-Entry Communication Highway for Superconducting Quantum Chiplets. This work is done in collaboration with Cisco Quantum Lab. Superconducting platform is one of the leading candidates for quantum computing. However, it is hard to build a giant superconducting chip because as the size of device increases, qubits would become less controllable. There would be more crosstalk and the yield rate would also decrease. Therefore, we need a modular system which connects processors together with short-range or long-range links. With the short-range connections, we can have the chiplet architecture, and with the long-range connections, we can have the distributed quantum computing. In this work, we focus on the chiplet architecture. With the increased computing scale comes the increased routing distance in communication between qubits. Compared with monolithic computing, the swap-based routing becomes inefficient due to the long routing distance. Moreover, the cross-chip links are usually more error-prone than the on-chip ones, and this heterogeneity is not considered in monolithic computing. Compared with distributed computing, since the performance of short-range cross-chip connections are not as bad as the long-range ones, the number of remote gates should not be the only metric to consider in the chiplet architecture. Moreover, we cannot assume all-to-all connectivity between different processors as we often do in DQC. That being said, we still find it useful to borrow some communication protocols that are originally designed for DQC. For example, this is a protocol that enables concurrent control of data on multiple processors. It utilizes a GHZ state shared among different processors, which are shown in the deep blue. And in this example, the control qubit is Q1, and the 3-qubit GHZ states is on Q0, Q4, and Q7, each on a different processor. What we can do is we can apply a C0 between Q1 and Q0 and apply a measurement on Q0 followed by some poly corrections. In this way, the data of Q0 is shared with Q4 and Q7, and all these 3 qubits can be used as control on their processors. Once the control qubits are completed, we destroy the entanglement by measurements on Q4 and Q7, followed by a poly correction on Q1. The insight of our paper is that with the chiplet architecture, qubit resources are no more as scarce as in monolithic computing. Therefore, ancillary qubits become more affordable, and we can trade them for more program concurrency using the communication protocol we mentioned just now. This is an example of compiling the circuit on the left to the 3x3 chiplet array on the right, where the deep blue qubits are the highway qubits. The red, orange, and green gates are 3 groups of control gates sharing the same control qubit, which can be aggregated into multi-target control gates. With the highway protocol, the gates in red and orange can be executed concurrently through the highway. Then we move qubit 2 and qubit 5 close to each other by inserting swap gates so that the gates in black can be executed locally off the highway. After that, we prepare a new GHZ state on the highway so that the control gates in green can be executed concurrently through the highway again. Our contributions can be summarized at 3 levels. At the level of computing paradigm, we propose a hybrid model of gate-based and measurement-based computing, with the data qubits operating in a gate-based manner and the ancillary qubits operating in a measurement-based manner. In this way, we can prepare the GHZ state with parallel operations, and this is becoming practical with the advancement of mid-circuit measurement technology. Specifically, this is a circuit that prepares the GHZ state. All necessary 2-qubit gates are performed in only 2 rounds, followed by a round of parallel measurements, and an additional round of parallel C0 gates may be needed if we want to bring more qubits into the entanglement. At the level of communication mechanism, we abstract the ancillary qubits into a multi-entry communication highway. It facilitates efficient communication by enabling concurrent execution of control gates sharing the same control qubit, regardless of the distance between the qubits. We further reduce the qubit overhead by allocating a sparse highway structure with the interleaving highway qubits, while maintaining a dense structure at some critical points, including like crossroads and boundaries, to either reduce the latency or improve the overall fidelity. For example, the highway structures for square lattice and hexagon lattice look like this, where most part of the highway is in an interleaving structure. To construct GHZ states on the sparse highway structure, the circuit of entanglement preparation also changes accordingly, with the CNOT gates replaced by some bridge gates. The depth of this circuit increases a little bit, but it's still pretty parallel. At the level of program compilation, we fully exploit the highway resource with an efficient local and highway routing, as well as the dynamic scheduling. There are two challenges for the routing. The first one is to execute gates through the highway. The qubits of those control gates need to be adjacent to the highway. We refer to the process of routing data qubits towards the highway as local routing. In our compiler, we try to route each data qubit to a nearby highway qubit that enable its earliest gate execution. The second challenge is that the highway paths of different highway gates cannot overlap. Here, the orange gate is a highway gate consisting of 3 CNOT components, and they share a consecutive highway path. And the red is another highway gate, and their components share another consecutive path. But these two paths should not overlap each other. We refer to the process of allocating paths for highway gates as highway routing. In our compiler, we try to assign a highway path for each highway gate that maximizes the spatial path sharing between the different components within the same highway gate. For scheduling, the challenge is that the entangled states on the highway are periodically consumed by the execution of highway gates, and the preparation of new entangled states leads to an overhead. Our insight is that we can reduce this overhead with a dynamic highway period that maximizes the temporal highway sharing in each period. For example, if our highway has only a length 3 and we want to execute 5 control gates sharing the same control, we may want to do 3 of them first, which are the qubit 1, qubit 3, and qubit 4. Then we do the qubit 5, and at the same time we bring qubit 2 to the adjacent to the highway, and then execute it using the same GHZ state. In our compiler, we try to collect as many components as possible into the same period, so that the entanglement can be fully utilized before destroyed. We evaluate the framework with 2 metrics. The first is the circuit depth. We count each measurement as multiple depth, because measurements usually have longer latency than 2 qubit gates. The second is the effective number of CNOT gates. We count each measurement or cross-chip CNOT as multiple on-chip CNOTs, but because they usually have a larger error rate than the on-chip CNOTs. We evaluate the framework with some typical quantum benchmarks, including BV, VQE, QAOA, and QFT. We use the Qiskit compiler as our baseline with the highest optimization level 3. The results show that our framework significantly outperforms the baseline. Specifically, it reduces the depth by about 60% and reduces the number of effective CNOTs by about 20%. The evaluation also shows great scalability of our framework in the sense that as the number of chiplets increases, the improvement of both the metrics increases as well. Moreover, our framework has great generality as it can be applied to chiplets with various coupling structures, including square, hexagon, heavy square, and heavy hexagon. The result shows that it outperforms the baseline for all of these coupling structures. To summarize, our work explores a trade-off between the usage of qubit resource and the program concurrency. It demonstrates the improvement in the performance of quantum computing by taking advantage of the mid-circuit measurements, and suggests that maybe a hybrid computing model will be useful in the way of approaching a larger scale quantum computing. That's all. Thank you.
Questions? Yeah.
Thanks for your great presentation, Ravi from Georgia Tech. You mentioned that your baseline is the Qiskit compiler, but for QAOA, we have specific compiler, I think from David, which I noticed is there, and it significantly outperforms specific compiler. And I was wondering, how would you compare the result if the baseline, becomes the better baseline of the specific QA compiler?
Okay, we didn't do the specific optimization towards QA/OA, so we didn't compare with the baseline you mentioned, but we aim to provide a scheme for general circuits, so we just use the Qiskit compiler as a baseline. Yeah, maybe we need to compare with your the baseline you mentioned if we are on the specific problems just like QA/OA, but we didn't do that. Yeah.
Hello, I'm Chong from Seoul National University. Thank you for a great talk. I have a question about the appropriate price of the shorter quantum circuit. So I understand that your work buy shorter quantum circuit as a cost of more ancillary qubits. So then how many qubits can we pay for to reduce the depth of the quantum circuit? Do you have any standard for the price of the shorter circuit?
How many? Can you repeat your questions? Sorry. How many qubit?
How many qubits can we pay for to reduce the depth of the circuit?
In this, in our experiment, for example, this is the evaluation done with the square lattice, and on the last column, you can see the percentage of our highway qubits, and it's only about less than 20%. But with this qubit overhead, we can achieve much more reduction in the depth and the number of CNOT.
Thank you for your answer.
Any other questions? We still have like a minute. So. Right.
Hi, nice talk. Did you look at, I was wondering what the sensitivity of your result to sort of, essentially you have this highway, which is like a critical resource, right? Like did you consider like making it wider or having like...
Okay. I can show more results. Like you're thinking about whether we can make the highway wider and using more
parallel, yeah.
Yeah, so this may be a relative picture. I'm sorry. Can I? Yeah. So here we did the evaluation with different percentage of the highway qubits. So this is the original data I show in the presentation, and we triple the highway resource, and when we double it, the improvement increases a little bit. So this comes down, but when we triple it, we further increase the highway qubit overhead. It doesn't decrease too much. So yeah. So
interesting.
By doubling, I just mean from single lane to double lane, and by tripling from the triple lane.
Yeah, it might be interesting to look at. I was wondering maybe to try error correction protocols actually with your scheme.
Yeah, that may be
maybe ones that have, like high connectivity. Be interesting to see.
Okay. Yeah, that may be a good next step. Yeah. Thank you.
Yeah, let's thank the speaker again.
Thank you so much.
Sorry. Maybe connect the audio. I don't need actually for it. No, it's for the thing. Okay. So I can start? Yes. Yes, okay. Thank you for the introduction. I'm Siwei Tan, a PhD student from Zhejiang University. My advisors are Professor Jian Weiyin and Professor Li Qianglu. Today, I'm going to present our work to perform a fast and accurate quantum result calibration using the finite element method. Quantum result is operation that reads information from quantum bits to classical bits. With multiple sampling, the output of the result is a probability distribution of different measured bit streams. There are many sources of noise in the quantum computer. Among these sources, quantum result error is significant on current quantum hardware. For example, the readout error is around 400 times that single qubit gate error on the IBM quantum device and 5 times that of 2 qubit gate error on our custom 10 qubit quantum device. Here, we use the implementation of readout on the superconducting quantum device as an example. The readout is implemented by pulse sent into the readout line. By coupling the qubits and the readout line, the pulse takes the information of the qubit state out. We classify the qubit state by detecting the frequency shift of the pulse. Usually, qubits share the readout line in the quantum processor, making the frequency crowded and leading to high interactions. The readout noise can be categorized into 3 types: reductions error, excitation error, and crosstalk. The reduction and excitation errors make the qubit unexpectedly evolve from 1 to 0 or 0 to 1 during the readout. There are many works to introduce this error. Besides, as highlighted in recent works, interactions such as the crosstalk is a significant source of error. It originates from one qubit to another qubit. The interaction is more complex compared to other sources of errors. The effect of interaction is different when the qubits stay in different states, and they also varies in different combinations of measured qubits. This is because the frequencies of the interactions change on the different operations. For example, on the IBM Pulse quantum device, the readout error of qubit 1 increased by 0.08 when qubit 5 is measured or not. Under the crosstalk, the readout output of qubits has correlations similar to the entanglement, making the calibration of it difficult. To make it easier for us to understand the difficulty of the calibration, let me introduce a basic calibration flow based on the multiplication. For a readout, multiple samples will yield a probability distribution. This distribution can be represented as a vector equaling to the square of the amplitudes of the qubits. However, readout error leads to a perturbation in the probability distribution and noise result. Such perturbation is formulated as a linear transformation from the ideal distributions to the measured distributions. We can represent this perturbation as a noise matrix and multiply it with a noise measured distribution to calibrate the readout output. The size of such noise matrix grows exponentially with the number of qubits. For n qubit, the matrix dimension is 2 to the power of n. Matrix-based readout calibration consists of 2 steps. In the first step, we obtain a noise matrix by running a series of benchmarking circuits. These benchmarking circuits prepare qubits to different basis states and apply measurement. The obtained probability distribution is used to fill in the noise matrix. The element of i's chrome and j rows equals the probability that qubits are prepared into state I and measured state j. For example, the element of second column and the first row equals the probability that qubits are prepared into state 1, 0 and measured state 0, 1, which is 0.7 in the example. Then, for any measured distribution, we represent it as a vector and multiplying with the calibration matrix to inverse the readout noise process. Although the metric-based calibration is accurate, it suffers from high computational cost. The categorization requires executing 2 to the n circuits and calculate the inverse matrix with a complexity of 4 to the n. The calibration for the input also involves the complexity of 4 to the n. For 25 qubit calibration, the multiplication requires 8.8 TB of memory and 100 hours with high performance CPUs. There are many works that aim to improve the scalabilities, but they are still not fast and accurate enough to calibrate large-scale readout outputs. Here we list two represented work proposed by Google and IBM. IBM decomposed the real calibration matrix into multiple single qubit matrix, but ignores the qubit interactions, leading to a failure in calibrating 80 qubit readout outputs. M3 uses a spatial word method to prune the matrix, but is still limited by memory and requires 16 PB to calibrate an 18.5 qubit result as presented in their papers. Due to the challenge of the calibration, we propose a quantum finite element method based on the classical finite element method. Here, we show an example of classical FEM method to simulate the deformations of a sponge under compressions. As the force distribution of the sponge exhibit locality, FEM applies a divide and conquer strategy. It partitions the sponge into multiple lattices and analyzes each lattice independently. By iteratively putting the states of lattice all together, the evolutions of the sponge is analyzed. Our FEM method on readout calibration applies the same route with 4 steps. First, we partition Q into groups. And second, we analyze the noise in each group independently. To implement such FEM method, the mathematical formulations of QFEM is represented process with a series of subnoise matrix. In each iterate a part of the noise and iteratively mitigate the overall noise. We apply a method that trains the grouping schemes of qubits in different iterations. In some few reasons for providing fast and accurate calibration. First is fast because it adopts a finite with a divide and for different measured qubits. With approval such as IBU cannot characterize such variance of errors. Here, we can calibration and we generate the sub crosstalk variant. We use this matrix to calibrate the probability distribution. We generate the subnoise matrix based on the grouping of the first calibration of specific quantum device. First, we need to partition qubits to determine the grouping schemes. And second, we need to be the both based on a data set collected by running benchmarking circuits. This circuit prepared qubit to different basis. They have 3 possible operations on each qubit. 0 means set Z measured. 2 means qubit circuit nor some qubit being measured, which aims to maximize the variety of the readout. Back data, we can know the readout error rate of each qubit under different operations. You have mentioned that readout error of a qubit also depends on operation interactions. We define this interaction as the variance of qubit error on the different qubits operations among all qubits to build a weighted graph. Is a qubit and each edge is labeled by the interactions. Max cut solver to partition qubits. The partition aims to maximize a group, and such a grouping scheme ensures that in each iterations, the formulated subnoise matrix try to comprehensively capture the interaction to the real matrix. And here we also present an example of to make qubit in the same group. Like, for example, qubits that share the same readout resonate, and qubits that readout frequency, and also qubits that have over mapping in the shift region of the frequency observation. Another key noise matrix formulates the transformation probabilities from the ideal state to measured state. Following the same idea, the sub-noise matrix of QU and MEN also formulates the transformation probabilities of states inside the qubit group. The row index are the set of the set state and the real state of qubit. Besides, when considering the probability, we consider that some qubits are not measured to maximize the accuracy. And overall, put these two techniques together, you can do characterization for any measured qubits. In the characterizations, in the first iterations, we run benchmarking circuit to obtain the result, and we use this result to construct the weighted graph and partition qubits. Now we have the first groups sub-noise matrix for the benchmarking circuit output and calibrate them. After calibration, the outputs are closer to the ideal state, and the second iteration applies the same step and aims to characterize the remaining errors of the first iteration. And in the calibrations, given the measured qubit and the measured distributions, we can use the distribution and the grouping schemes from the characterization to generate sub-noise matrix and mitigate the error. In addition, there are many tensor products in the iterations which could be a bottleneck of the computation. We observe that a large number of sparse intermediate vectors are generated in the tensor product. We therefore build a sparse tensor product engines which prune small matrix values during the computation process. We observe this can reduce the exponential complexity to polynomial complexity in many cases. And we conducted experiments on 5 quantum computers from 4 platforms. And QEFEM reduced the calibration time of the 136 qubit program output from 100 hours to around 3 minutes. And we also show an average improvement in fidelity of 1.2 times and 1.5 times compared to the methods CTMP and IBU respectively. At last, we summarize the key points. First, we introduce the limitations of prior works. They are not fast and accurate enough for large-scale quantum results as they have a high-dimensional noise matrix. Second, we introduce how to use the finite element method to improve the scalabilities. And third, we introduce 2 key techniques to partition qubits and generate a noise matrix. We also design a sparse tensor product engine to speed up the communication. Okay, thanks for your listening.
Hi, so I was wondering when you look at the final experiment and you measure the fidelities,
Yeah.
are you looking at computational states or more general states?
What is a, sorry, I don't know, what is a computational state?
Like 001, 010, or are you looking at something like +00? Do you consider those states?
We get the distributions. I just calculate the Hellinger distribution, Hellinger fidelities between the we measure the distribution and the real distribution.
Yeah, for the real distribution, are you preparing only computational states, like the bit string states, or are you considering more general quantum
I
states?
just compute the basic
Only computational
yeah,
states.
only the computational state. Because
Okay.
when we measured, we only get the distribution.
Okay.
We do not get the state back.
I'm wondering if this like kind of matrix kind of model doesn't work for more general states. I'm not sure if you looked into that.
Yes. Yes, maybe it can be applied for some like the tomography to further improve the fidelity. Is your
I'm saying like if you can prepare a more general quantum state, which is not a computational state, you look at that distribution, what you expect and what you measure. Have you tried looking at that?
sorry, actually I haven't.
Okay, thank you.
Any other questions? Okay, maybe I can ask just one more. So can you say a little bit about why your like your complexity or your computational time is less than the MC model, because MC is like matrix free, right? So
Yes.
yeah, I know you mentioned MC earlier.
Yes, yes, sure.
Where-
Because in M3 we have a Hamming threshold, and we need to define a threshold. For example, when we define the threshold in 3, it means when we get the output it's a many bit string, we only consider that the error will make it to another bit string in Hamming distance 3. And this we can calculate the combinations of this Hamming distance. For more qubits, it will become CN3, and it will increase very fast. And they also have formulations in their paper in the appendix for about 80 qubit. They have C83 and C82 plus C82 and plus C81. It will become very, very large.
Okay, thank you. Let's back to you. Okay, next we have Yuan from Albert, scale distributed.
Hello everyone, I'm Junpyo Kim from Seoul National University. In this talk, I present a fault-tolerant million cubic scale distributed quantum computer. This work was done with my fellow student and my advisor, Professor Zhang Kim. Quantum computing can innovate the entire computing paradigm in various areas. However, practical applications require thousands of logical qubits, and each logical qubit again requires thousands of noisy physical qubits. Therefore, we need a fault-tolerant quantum computer with millions of physical qubits. Let's begin with how the fault-tolerant quantum computer minimizes the logical qubit errors. Fault-tolerant quantum computing, or FTQC, runs error syndrome measurement and error decoding to minimize the logical qubit errors. In FTQC, we encode a logical qubit as a logical qubit patch, which contains thousands of noisy physical qubits. First, error syndrome measurement, or ESM, finds the hint of the error locations. It entangles and measures the physical qubits and extracts the hint of the error location called error syndrome. The second step is the error decoding. Taking the error syndromes, the error decoder first pairs the syndrome and identifies the exact error locations. Note that to achieve low logical error rates, FTQC requires low error rate for ESM, fast error decoding, and accurate error decoding. As I mentioned, we need a million cubic scale quantum computer to realize FTQC. Multi-dilution refrigerator system, or multi-DR systems, can support millions of qubits by providing a large cooling capacity. A large cooling capacity is extremely important because even state-of-the-art designs cannot achieve 50,000 of qubits due to the huge cryogenic power dissipation and limited cooling capacity. Multi-DR systems can solve this cooling power problem by scaling the cooling capacity with more DRs. In the multi-DR system, we use entangled qubits called EPR pair for DR-to-DR interaction. However, multi-DR systems characteristics incur huge ESM error, slow decoding, and inaccurate decoding. The first characteristic incurs huge ESM error. In the multi-DR system, we can only use EPR pairs for DR-to-DR interactions. So it requires many additional gates and long latency to build a DR-to-DR two-qubit gate using EPR pair. As a result, the multi-DR systems suffer from the high ESM error rate. The second characteristic incurs slow decoding. In the multi-DR systems, due to the long communication delay between DRs, it needs long time to send error syndromes to different DRs. This long communication delay significantly slows down the decoding. If the decoding speed is lower than the syndrome generation speed, the system fails with the increased logical error rate. The third characteristic incurs inaccurate decoding. In the multi-tier systems, diverse error patterns occur from millions of noisy physical qubits. However, as the current error decoder runs with only one fixed setup, its decoding is not accurate enough to handle all the different error patterns occurred from millions of qubits. In summary, the multi-tier systems suffer from the huge logical errors due to high error rate for ESM, slow error decoding, and inaccurate error decoding. So, our research goal is to realize a fault-tolerant million cubic scale quantum computer with low enough logical error rates by resolving all the challenges. Specifically, the naively scaled system suffers from a logical error rate of 1 due to the 3 problems. To resolve the problem, we propose low error ESM sequence, fast error decoding, and accurate error decoding. With the solutions, we achieve a low enough logical error rate that can run practical applications without errors. From now on, I will introduce our multi-tier aware FTQC solutions. To achieve the research goal, we propose 3 low error ESM solutions, 2 fast decoding solutions, and 1 accurate decoding solution. From now on, I will introduce the solution for a low error ESM sequence. Due to the time limit, I will only show the first solution because it minimizes the errors the most. To achieve low error ESM, we propose quantum classical hybrid ESM. First, previous work suffered from high ESM error rate as they use distributed CG gate. Ideally, the ESM applies 4 CG gates to adjacent data qubits. In the actual multi-tier systems, the ancilla qubit and data qubits are placed in different DRs. So, the previous work proposed a distributed CG gate using EPR pair. However, it suffers from high ESM error rate due to too many additional gates and long latency. We greatly reduced the ESM error by offloading the overhead of distributed CG gate to the classical computation part. First, we observed that we can replace a CG gate into a classical XOR if the CG gate is just before the 2 measurements. With this observation, we place 2 ancilla qubits entangled to each other and modify the ESM. In the modified ESM, we apply the distributed CG gate on the ancilla qubits just before the 2 measurements. Then, we reduce the overhead by replacing the distributed CG gate to a classical XOR. By doing so, we reduce the ESM error rate by 2.4 times thanks to the minimized number of gates and latency. Next, I will introduce our 2 fast error decoding solutions. The first solution for fast decoding is parallel error decoding. The problem is that the existing decoders are very slow as they find errors sequentially. Specifically, our baseline is the recent SPI-fast error decoder, which is the fastest and the only hardware decoder supporting logical operation. It sequentially selects one syndrome as a decoding target and finds the closest syndrome to decode the errors. If we allocate 2 targets for parallel decoding, the decoding may fail with the collision. Therefore, the baseline currently decodes errors sequentially. We greatly reduce the decoding latency with our parallel 9-patch granular decoding. We enable the parallel decoding without collision by changing error decoding sequence. First, we observe that the length of the valid syndrome pair is always shorter than the half of the code distance according to the definition of quantum error correction. Therefore, for each decoding, we only need to search within 9 adjacent patches as a valid search space. With this observation, we allocate different decoders for 9-patch granularity. Then, each syndrome search space does not overlap to each other. By doing so, we fully parallelize the decoding and achieve 8 times higher speed. To further reduce the decoding latency, we propose synchronization-free error decoding. Currently, the long communication delay slows down the decoding of boundary patches. For the patches far from the boundary, the decoder can decode them in a full speed because the syndrome search space is within a single DR. However, For the boundary patches, we must synchronize two decoders every clock cycle because the syndrome search space is distributed across 2DR. It significantly slows down the decoding of the boundary patches by making the clock frequency bound to the communication latency. We greatly reduce the decoding latency with synchronization-free boundary patch decoding. To break the synchronization without collision, we handle three types of patches differently. First, to remove synchronization between the boundary patches, we place a boundary decoder and gather every required information. Then, the boundary decoder can run in a maximum clock frequency. Second, because patches far from the boundary or independent to the boundary patches, we decode them in parallel with boundary patches. Third, because the boundary adjacent patches are dependent to the boundary patches, we decode them after the boundary patch decoding to prevent collision. By doing so, we break the synchronization without collision and achieve 67 times higher speed. Finally, we propose ensemble error decoding for accurate error decoding. The existing spike-based decoders are inaccurate because the decoding results are extremely sensitive to the setup. Despite the setup sensitivity, the baseline currently runs with only one fixed setup. The decoding result changes with the decoding target allocation order. For example, in one syndrome pattern, the decoder with forward order generates the correct result. However, in another syndrome pattern, the decoder with reverse order generates the correct result. Therefore, the baseline has low accuracy due to each single setup execution. We achieve high decoding accuracy by reducing setup sensitivity with ensemble error decoding. Our decoder runs 8 different decoders with different setups and ensemble those results to reduce the setup sensitivity. First, when the syndrome comes, 8 different decoders process the same syndrome pattern with multiple setups. Then, the ensemble error decoder selects the most probable result by comparing the total pair length. As a result, we reduce the setup sensitivity of the spike-based decoder and increase the decoding accuracy by 10 billion times. From now on, we evaluate our multi-tier aware FTQC solutions. Let me first introduce our evaluation methodology. First, we target to achieve the logical error rate of running FemoClo with 99% success rate, which is a practical and classically intractable quantum application. Second, for solid evaluation, we use full-stack quantum computer simulators, XQSIM and QISIM. Let me show our evaluation results. The graph shows the logical error rates with different combinations of our solutions. First, with our low error ESM, fast decoding, and accurate decoding solutions, we reduce logical error rate by 10 trillion times and achieve the target logical error rate. Note that all the solutions are important to realize our research goal. We cannot achieve the target logical error rate without any one of our solutions. This is the last slide of my presentation. I will summarize my talk as follows. This work is the first to realize a practical million cubic scale quantum computer. For this purpose, we identified the unique challenges in the multi-tier system. Next, we propose 6 novel ESM or error decoder solutions to address all these challenges. Lastly, with our solutions, we reduce the logical error rate by 10 trillion times. Thank you for listening and feel free to ask any questions.
Hi, Suhas from Georgia Tech. So I have 3 questions, but I'll probably ask 2 for time reasons. First thing, I was wondering about some of the assumptions you made in the paper. So specifically, if we're looking at the decoding latency of the patches you selected, how often are we decoding 9 patches at once? Because in principle, if the 9 patches are not connected, we can decode them all in parallel. Do you have any insights regarding that?
Thank you for the great question. We are considering actual logical operation, which is logic surgery. And in the logic surgery operation, we have to merge multiple logical operation and made all the logical patches connected.
Yes, I understand that, right? But how often are all 9 patches connected with each other?
Okay. I understand the question. We are assuming that, we are assuming the operation that, one split and one merge, one split, one merge. And when the split operation, then all logical operations are splitted. And when the merge operation, then all logical qubits are connected. And so it is theoretically the split merge. Yeah,
Okay, my second question, right? Okay.
Yeah, take it off.
Hi, nice talk. I'm Nargis from Georgia Tech. I was wondering, how did you consider also the types of error that are specifically for the communication between the multiple quantum computers, for example, attenuation or the decoherence that might happen when the communication happens between multiple quantum computers? How did you consider those as well?
Great point. Actually, there is some experiment data from other previous works, and we gain some error rate, abstract error rate from the previous works, and we use those values in our simulation, in our evaluation.
Yeah, thank you.
Thank you.
Silent speaker. So the last talk is pro-match, extending the reach of real-time quantum error correction with adaptive breeding. The audio.
Yeah.
Do it over on this thing, and yeah, can you do the play now and then connect it? All good?
Yeah. 1 second. Hi, I'm Nargis, and today I present ProMatch, which is an adaptive pre-decoder that extends the reach of quantum error correction. This work is in collaboration with the high error rate. There is a billion X gap between the error rate that we want for larger scale applications and the one that we have currently in the device level. It is very unlikely that we bridge this gap in a device alone. So to close this gap, we need quantum error correction. In this work, we focus on surface code. And in quantum error correction, a logical qubit consists of data qubits. Several data qubits. And to detect error in these data qubits, we have parity qubits. When an error happens in a data qubit, its adjacent parity qubit flips. To perform error correction, we periodically measure these parity qubits, forming what is called as a syndrome. This syndrome is sent to a decoder to identify the location and types of errors. This process of quantum error correction happens repeatedly again and again, and this process needs to be done in a short amount of time so that the errors won't accumulate. The time available for decoding for superconducting is 1 microsecond. Decoders that can finish within 1 microsecond are called real-time decoders. Surface code decoding is a well-studied problem, and the gold standard for decoding it is called minimum weight perfect matching. Minimum weight perfect matching is a graph-based algorithm that is complicated, but it is often used to determine the bounds of surface code. This graph shows the logical error rate of surface code as distance or the redundancy of the code increase from 7 to 13. As minimum weight perfect matching is complex, it is hard to do it in real time. The best real-time decoder that we have so far is Astria from ASPLOS'24 that works up to distance 9. After distance 9, there is a gap which increases significantly as distance increases. So the goal of this work is to have accurate real-time decoder for up to distance 13. The complexity of decoder depends on the Hamming weight of the syndrome, which is the number of flip parity bits in the syndrome. The number of perfect matching scales exponentially with the Hamming weight. For example, if you have only 2 flip bits, the syndrome if you have only 2 flip bits in the syndrome, there's only 1 matching that can happen, and the intervening data qubits are deemed to have error. If Hamming weight is 4, there are 3 options. For example, C can go with D, E, or F, and the other 2 get matched with each other. For 10, it's 945. This is still within the range of brute force search, and this is exactly what Astria does. But beyond this, for example, if the Hamming weight is 16, the number of options is 2 million. Way outside the range of practical searching. So we call these Hamming weights of more than 10 high Hamming weights, and for less than 10, we call them low Hamming weights. So notice that the complexity of real-time decoding mainly comes from these high Hamming weight syndromes. Now that we understand the complexity of decoding, let's see what happens in distance 13. This graph shows the Hamming weight distribution for distance 13, and the red line is the logical error rate with ideal minimum weight perfect matching. We can ignore this Hamming weight because the probability is low and they won't impact the logical error rate. But we still need to cover up to distance 32. Can you imagine how the search space, how large is the search space? Orders of quadrillions. It is very unlikely to have a real-time decoder for such a huge number. But we know that these low Hamming weights are covered by Astria in real time. And our challenge is this intermediate between 10 and 32. Can we enable real-time decoding by converting these high Hamming weights to low Hamming weights? The answer is yes. We can use a pre-decoder. Instead of having only a single decoder, we can split the problem into 2. Consider a syndrome that has Hamming weight of 12. We cannot do this in Astria, but we can have a pre-decoder that, let's say, it pre-decodes 2 pairs. Now, the main decoder needs to only decode Hamming weight of 8. Astria can do this. So by using a pre-decoder, the main decoder gets a syndrome with a lower Hamming weight, which can be decoded easily. Pure pre-decoders play a game of accuracy and coverage. They all match flip bits in a static way regardless of the main decoder's capability.
They either play a risky game to get very high coverage by keep pre-decoding. But the problem is that even if a single pre-decoding is wrong, the whole decoding process for this syndrome fails. This results in a low accuracy. On the other hand, some pre-decoders are too conservative. They only pre-decode if they are very sure about the matching. This results in high accuracy, but low coverage. The rest is not manageable in real time. Our insight is that instead of a statically pre-decode, we adaptively pre-decode such that we have high accuracy and just good enough coverage. So we propose ProMatch, which has just sufficient coverage. It pre-decodes bits and then check if the Hamming weight is decodable by the main decoder or not. If not, it continues pre-decoding until the rest of the syndrome can be decoded by the main decoder. So given a Hamming weight, we exactly know how many bits we need to pre-decode, but which one we should do first, that matters for the accuracy. So we should always start with the one that are safest and then gradually go for less safer ones. Let me tell you an example. ProMatch applies a greedy method. A low-risk matching that is prioritized first are the pairs that have no other flip bits in their neighborhood. So these isolated pairs can be matched with each other with low risk. If low risk alone is insufficient, we start decoding more complex patterns. For example, here consider we have two flip bits. Node 2 has 4 options. If node 2 get matched with node 3, then 1 and 4 need to be paired with something far apart. We call these nodes with no adjacent nodes in their neighborhood singletons. We should avoid singletons because they add more weight to our solution and they are more likely to be pre-decoded inaccurately. If ProMatch sees such a pattern, it tries to avoid generating singletons. For example, if 1 get matched with 2, then 3 can get matched with its nearby 4. If medium risk is still insufficient, we go for more complex patterns. As an example of high risk, for example, look at this. These 2 can get matched with each other, or these 2 can get matched with each other. There's up to 50% likelihood that our pairing could be wrong. So we only do this if we absolutely need it for coverage. To summarize, ProMatch start with safer matching to keep accuracy high and adaptively makes more risky decision till reaching the sufficient coverage. Depending on the risk level of matching, the required pre-decoding time would be different. First, if the Hamming weight is less than 10, the whole thing can be done by Astria. But if the Hamming weight is more than 10, and we only need to do low-risk matchings, and we can get to Hamming weight of 10, we still have enough time for pre-decoding. If you go for medium-risk matching, we need more time for pre-decoding. So the main decoder, it doesn't have enough time for do all the Hamming weight 10. So we target the main decoder to do only Hamming weight of 8. If we need to go for high risk, we need even more time for pre-decoding. So we target the main decoder to do only Hamming weight of 6, which can be done in short time, and we have enough time for pre-decoding. So ProMatch adaptively changed the decoding and pre-decoding time budget to decode the whole syndrome in 1 microsecond. This graph shows the Hamming weight distribution before and after ProMatch, and it shows that ProMatch always reaches the sufficient coverage by reducing the Hamming weight of syndrome to less than 10. And here we can see the minimum weight perfect matching logical error rate for distance 13. A state-of-the-art real-time decoder has a gap for this distance with ideal minimum weight perfect matching, while ProMatch always outperforms it for all this physical error rate. And if we run these two real-time decoder in parallel and choose the one with the lowest weight, we reach minimum weight perfect matching logical error rate for distance 13 and physical error rate of up to 3 times 10 to the power of -4. We also synthesize this on FPGA and it has low hardware overhead. So to conclude, large-scale quantum applications need large distance codes, and real-time decoding for this large distance code is challenging, mainly because of high Hamming weight syndromes. MECH solved this by adaptive pre-decoding with high accuracy and just sufficient coverage. So this work enables real-time decoding for surface code up to 13. Thank you, and I would be happy to get any questions.
Hi, nice talk. I have a clarification question on the baseline from the last slide. So you have Astria as one of the baselines. So I remember that Astria is an exact MWPM decoder. So why is it worse than MWPM in this case?
That's a good question. Astria has another version, which is Astria G. Astria does exhaustive search. For Astria G, it's a near exhaustive search. It is for distance for distance 9, which the number of which the Hamming weight, like the number of options given the Hamming weight, will be more than the thing that we can do in 1 microsecond. So Astria G, it do some types of pre-matching, and then if the Hamming weight reach to 6 or 10, it sends it to Astria. So this is for Astria G, another version of Astria.
Thanks. And I have a quick follow-up. So are Astria G and ProMatch better than Union Find in terms of accuracy?
Minimum weight perfect matching, in general, it has a better threshold compared to Union Find. So because we reach minimum weight perfect matching, logical error rate, it is better than Union Find.
Okay, thank you.
Sure.
Any other questions? Okay, just fine. So that's the end of the session.